Welcome to another lecture session of this video lecture series in Applied Physics UPA 004 course. And in this series, we are talking about thin film interference. And today we will talk about Newton's rings and some of its applications. So the Newton ring is basically an application by itself of the thin film interference, where the thin film that is involved is a wedge-shaped thin film. And we have already discussed the interference in case of a wedge-shaped thin film in the last lecture. So today we will talk about how the Newton's rings forms. Then we'll try to derive a expression for the diameter of the Newton's rings. Then we'll check how the Newton's rings can be used for measurement of wavelength of monochromatic lights and the refractive index of liquid mediums. So here is an example of such Newton's ring, and here is a schematic diagram of the phenomena of Newton ring, where you have a light source, a monochromatic light source, and then this is the actual setup for the Newton's ring, and this is a glass plate, this is a traveling microscope. So here is a actual snapshot of a Newton's ring setup. So this is the sodium lamp. From here the light goes into this setup, and this plano-convex lens setup is right here. This is this glass plate. If I could enlarge it, probably it would be better. So here is a bigger version of this same photograph, where this is the sodium lamp and this switch is to power on the sodium lamp. Then the sodium lamp, the yellow light is forwarded to this setup here. This is the glass plate, and down here is a plano-convex lens setup, and here is the traveling microscope, where during the experiment you look from this side and then the interference is happening here. So the Newton's rings are formed here, and you look at through this microscope and you see nice interference patterns. Now, to understand the formation of Newton's rings, we have to first understand what is this plano-convex lens and where does this thin film or wedge-shaped thin film forms. Now, to understand the plano-convex lens setup, now a plano-convex lens setup is like this. So there is a plano-convex lens, and then there is a glass plate, plain glass plate is there at the bottom of this plano-convex lens. Then what happens is this radius of curvature of this plano-convex lens, this curvature of this surface, let's say this is the center, and so this is the radius of curvature. This radius of curvature is taken to be very, very large, so that this curve actually in a real experiment would be very, very flat and more or less same to a plane surface. So when that happens, then this thickness here becomes very, very small. So thickness is the largest on the edge of this plano-convex surface and 0 at the center where it is touching the lower glass plate. So that's how a wedge-shaped thin film is formed. Now, to understand this, let us look at how this plano-convex lens is formed. So basically, to form a plano-convex lens, what you do is you take a big, huge glass sphere, and then you take a part, cut it out. So this part becomes your plano-convex lens, right? So if you look at from the top, from this side, what you would see is this is like a circular lens with some radius. So this radius is this distance, and radius of curvature of this surface here is the radius of this original convex surface. It's the radius of the original sphere from where this part was taken out. So here, this point is the point where the plano-convex lens touches this surface, bottom glass plate, plane surface. Now, as you move away from this point, so that means as you are moving away from this point in different directions. So here is a region, then at this different distances from this origin, the thickness is same on all these circular points. For example, let's say this point here is this point, let's say this circle is called A. So this is A. Then this point here is this point. So this point is called B. And this point here is called C. Now all these points along different directions on these different circles are equivalent. So if you take these points, then they are all equivalent. Why I'm talking about this? Because it will come at a later stage that you have to remember that thickness of this wedge shaped thin film here at, let's say, A is same all around this circle. Then the thickness at the point B, which is a little larger than what was at the point A, is also same around this circle. Then thickness at C, which is again a little larger than point C, is again same for all these circles, all these points on this circle. So here, let's say this is the point A, this is the point B, this is the point C. So then the thickness on the left hand side at these different points A, B, C would be same as the thickness at these points A, B, C on the right hand side and in all directions similarly. Now, so that's point number one. You have to remember that throughout this plano-convex lens, there are these concentric circles where the thickness of the wedge is same, and this thickness increases as you go away from this touching point, either this point or this point, towards the edge of this plano-convex lens. So now how the interference is happening? Now to look at, so there is this plano-convex lens sitting over a normal plain glass plate. This is the only point where it is touching. Now a light falls onto this surface. This is our incident light. Then it's get refracted, comes to this point. Then again one part of it gets refracted, and then it gets reflected from the bottom surface, and then it enters the lens again and then goes out like this. So let's say these points are A, B, C. Then from this surface there will be another ray which is getting reflected back. Let's say this ray is this. So this is our incident ray. Let's say 1, 2, 3. So these two rays, 2 and 3, when looked from this side, you would see they would interfere and produce an interference phenomena on this surface. So likewise, there are lots of parallel rays coming in, and they are all meeting at different points on this plano-convex, on this surface, and they would interfere and produce interference. Either they would interfere constructively or destructively along this surface. And when you looked at from the top, from here, when you look at from this side, then you would see that there are places where bright fringes are formed. There are places where dark fringes are formed. So now to understand where dark fringe would form and where bright fringes are to be formed, then we have to look at this ray 2 and ray 3, which are actually the interference rays. So we have to find out what is the optical path difference between ray 2 and 3. In the last lecture for a wedge-shaped thin film, we have evaluated this condition. Let's say at this point D, the thickness is D, then the optical path difference is 2 mu D cos R plus theta, where this R is related to the refraction angle which is happening here, and this refraction angle can be calculated from this incident ray, the incident angle. Then this theta is this wedge angle, and as we explained earlier, if this radius of curvature of this surface, if this R is taken to be very, very large, then this wedge angle will be again very, very small. You have to remember this, because we will come back to this point again a little later. Now, this is the optical path difference. If you remember in the last lecture, there is another path difference which is lambda by 2, and that lambda by 2 is because the ray 3 here is getting reflected from a denser medium, coming from a rarer medium, assuming that this is some rarer medium like air. So this wedge is filled with air only, and this is, let's say, glass. So when a light reflects from a denser medium, then there is a phase difference of pi is introduced between the incident ray and the reflected ray here. Now that pi phase difference between 2 and 3 translates into a path difference of lambda by 2. So this is the path difference, total path difference between ray 2 and 3. Now for this 2 and 3 to interfere constructively, you would have the maximum condition to be 2 mu d cos r plus theta plus lambda by 2 is equal to constructively, so n lambda. And for destructive interference, so that they form a minimum, you will get 2 mu d cos r plus theta, this path difference lambda by 2, this total path difference is equal to 2n plus 1 lambda by 2. We have already talked about this in another lecture for the wedge-shaped thin film. Now let us simplify the things a little bit. Simplification. What are the simplification? That if the light that is incident is normal, for normal incidence r is equal to 0. Incident angle for normal incident angle is 0, so reflection angle will also be 0. Then for a very thin wedge, theta would be very, very small. When would that happen? So this basically r is large. So in that case, let's say what would be the minimum condition? That would be 2 mu d. So r is 0, theta is very, very small. So both of them could be very close to 0. So cos very close to 0 is 1. So you get lambda by 2, 2 mu d, lambda by 2 is equal to 2n plus 1 lambda by 2. And this implies for destructive interference, you have 2 mu d is equal to n lambda. Similarly, for maximum condition, this is the minimum condition or dark fringe, this is maximum condition or bright fringe. From there you get 2 mu d, so cos r theta plus 1, cos r plus theta is again 1 plus lambda by 2 is equal to n lambda. This would imply 2 mu d is equal to 2n minus 1 lambda by 2. So these are the two conditions for bright and dark fringes. Now also for our convenience, let's give these d's some name. Let's say dn. What is dn? D suffix n. What is dn? dn is like for the planar convex lens, if here is the point where the interference is happening, then this thickness is dn. So that's like the nth bright or dark fringe, and at that point this thickness is dn. Now next we would calculate this dn in terms of the radius of curvature of the planar convex lens. Next we will calculate this dn in terms of the radius of curvature of the planar convex lens. So let's say our planar convex lens is this. So this is the part we took out of the glass sphere and formed our planar convex lens. And this is the center. And let's say our glass plate is, here. So the glass plate is A, B, C. And then at some point here, this point where the ray 2 and 3 are interfering, then this distance is our dn or d. Now let us form some convenient diagrams, and now let us form some geometric diagrams. Let's say this point is P, Q, and this point here is n. Now this is the radius of curvature of this convex surface or the radius curvature of the sphere. Now from the properties of the sphere, we can write QB into QD is equal to PQ into QN. So what is QB? QB is D. QD is 2 into R minus D. PQ is R into R. So from here we get R square is equal to 2dr minus d square, which is very close to 2dr. So R square 2dr. Here what we did, we very small, because we are saying that this radius of curvature capital R is very, very large, so that this wedge that is forming here is very, very narrow. So this thickness dn is actually very, very small. So when you have a very small thickness, and if you take a square of it, then it becomes much smaller. So we ignore this d square compared to this term where r is very, very large. So this is capital R. So that's r square. Now again, for this point n to be dark means at this point n there is a destructive interference. The condition was 2 mu d n is equal to n lambda. So here this value of this d, we put it here, you get 2 mu r square by 2r is equal to n lambda. That implies r square is equal to n lambda r divided by mu. So this is the radius of the nth dark fringe. So that radius is distance from this point B, which is the point where it is touching the lower surface. Similarly, if this point n to be bright, then from the above condition earlier, we have 2 mu dn is equal to n minus 1 lambda by 2. So from here you get rn square is equal to 2n minus 1 r lambda by 2 mu. So this is the radius of the bright ring, this is the radius of the dark ring. So one thing may not be at this moment still not clear why we are saying that this is the radius of a dark ring. I already have explained a little while ago that if you look at from this side, from the top, what you see, this planar convex setup is a circle here, like a circle here. So this is the touching point, and all these points on this circle has the same radius, so same thickness. All these points on this second circle has the same radius, so the same thickness. So if a bright interference is happening here, constructive interference at the point P, then all the points on this ring will be bright constructive interference because they have the same radius, same thickness. Condition is same. Similarly, if this point C is where a dark fringe is appearing, then all the points along this circle will be again dark. So that's why these Newton's interference pattern are in the form of concentric rings, and at the center that's the smallest ring, and then as you go away from the center here means where the planar convex lens touches the lower surface, as you go away from the center the radius increases, and for different radiuses they would be either bright or dark and so forth, following these two conditions that we just derived. So these two conditions would give you at what radius or which circles would be bright or which circles would be dark. Now generally in Newton's ring experiment we don't talk about the radius, we talk about the diameter. So correspondingly the diameter can be calculated by saying that the diameter is just double of that. So if these are the rings, then for a ring nth, let's say this is nth ring, the diameter dn nothing but is equal to 2 of rn, and you place this into these two conditions. So now with this expression for the diameter, the dark ring diameter would be dn square 4n lambda r by mu, and from here for the bright rings the diameter would be 2n minus 1 to r lambda divided by mu. So these are the important results for the Newton's rings. Now this Newton's ring has very, very important applications. The first application is the measurement of wavelength of light, and that is a monochromatic light, and that, let's say, this wavelength is lambda. How to measure this? So with this Newton's ring setup, we measure the diameter of different rings. So let's say the diameter of nth dark ring is given by, similarly diameter of n plus pth ring, and that is a dark ring, would be dn plus p is equal to 4 n plus p lambda r by p. And then where p is just some integer. So it's like if this is the diameter of the 10th ring, this would be diameter of the 12th ring. In that case, the p would be 2. So then you take the difference of these two. The difference of these two diameters would be is equal to 4p lambda r by b. And then you can use this expression to calculate the lambda. Lambda is dn plus p square minus dn square divided by 4p r. Then application number 2, measurement of refractive index of a fluid, mu. So to measure the refractive index of a fluid, what you do is you do it in two separate steps. Step A, do the experiment with air in the wedge. So it's like if this is the wedge, so this is the plano-convex surface. So you do in one case with air, and then you measure this dn plus p square minus dn square is equal to 4pr lambda, just from the last expression. So you calculate all these dn, so it's like you calculate the difference between d10 square minus d8 square, then you calculate d12 square minus d10 square, and so forth, like several values with p is equal to, in this case, is equal to 2. So you do this a few measurements and keep a note of that. So that measurement would be is equal to 4pr lambda. Then you do that, you replace this air with a liquid. Let's say you want to find out the refractive index of the water. Then you replace this air with water. You put some water. You put a droplet of water on this lower surface, and then place the plano-convex lens on the water. So now the wedge would be now filled with water, and in that case you will have dn plus p. Again, you measure these diameters with the water itself. So let's say these diameters are now a little changed. Of course, that would change, and that would be 4pr by lambda divided by mu. So here we have neglected this mu because for air this mu is equal to 1. Now if you take the ratios of these two, take the ratios, then you get mu is equal to dnp square minus dn square dn prime square minus dn prime square, right? So this is the expression that you use for measuring the refractive index. So again, in short, for measurement of wavelength of a monochromatic light, with the given monochromatic light for which you want to find out the wavelength, you do the Newton's ring experiment, and then you find out these different diameters of the rings. So let's say you recorded diameter of the 10th ring, 11th ring, 12th ring, 13th ring, 14th ring, and so forth. And then you use the differences of the ring's diameter squares and equate with this number, and from there you get the value of the lambda. Here, of course, if we use the air as the medium, then mu is equal to 1. If you use some other medium, then you correspondingly use that refractive index here, with the assumption that you know the refractive index of this medium that you are using. Otherwise, you can just use air. So there is nothing between the two convex glass surface and the plain glass surface. So it's just simply air. In that case, mu is equal to, you can replace that to be is equal to 1. Then for the measurement of the refractive index of a medium, we do the experiment in two steps. First, with the air, you calculate this difference of the squares of the diameters of the different rings, and then you place the medium for which you want to calculate the refractive index, and then you calculate the same diameters differences and take the ratios, you calculate the refractive index. So with this we finish this lecture session. So in this session, to summarize what we did, we first tried to understand how the Newton's rings are formed, then we calculated the diameter of the Newton's ring, and then we calculated the expression for the wavelength and the refractive index that you can use for Newton's ring experiments. Thank you very much.